Hi, everybody. So, in part two of our calculus corona project, we're going to look at what's called the SIR model. The reason for the SIR model and the reason that we're looking at this is because you probably noticed when we tried to model the number of infected people or the number of cases of a virus spreading using just an exponential model or just a logarithmic model, we could fit the data quite well initially. But the problem with those models is they're only going to predict things a little bit ahead, maybe 1 day ahead, maybe 2 days ahead. And we know that at some point, the number of infections is going to end up turning around, that we know that the graph is going to hit a high point and then it's going to turn around. So an exponential function and a logarithmic function really don't work well because they don't turn around. So we can never really anticipate when that important turning point is going to happen. So this next way of modeling things is a little bit more advanced than what we've done, but it is the simplest model that people that really do this for a living, the simplest model that they work with. And so we're going to start with this. So the reason that this is called the SIR model is because it stands for, and I'll try to keep the color scheme here with red, blue, and green respectively, so that you can try to really make sure that you understand how the things to go together, because it can be a little bit confusing with all of the different variables. But the idea behind this is that you have an S function. S is a function of time, and it represents the number of susceptible people. The number of susceptible people, we'll call them the susceptibles. Now, usually this is going to start with the entire population being susceptible, but it's possible in some situations where you could have a vaccine, you could have half of the population is not able to get this sickness, either due to age or gender or being previously vaccinated, different things like that. So it's possible for the susceptibles not to be the entire population of a place. But with the coronavirus, it does appear to be the entire population, at least to begin with. But the idea is that we also have other functions here. The I function is going to be also a function of time, and this is the number of infected people. And so you can picture, as the number of infected people go up, the number of susceptible people is going to go down, because those infected people were taken out of the pool of people that were susceptible. They're no longer susceptible because they've already been infected. And our third function here is going to be the R function, which stands for the removed or recovered people. So we could call this the number of removed. I prefer removed because it's possible, unfortunately, that people did not recover from this disease, that they actually passed away. And so we're just going to call this the people that are removed from the population. They're removed really from both the susceptible set and the infected set. They have to be in a different grouping because we're assuming that once you have gotten this virus and recovered from it, that you're no longer susceptible, that you don't go back into the susceptible, that you can't get it again. Now, even though we're unsure about this, from what I've read, all of the other coronaviruses work that way. So the people that know a lot more about this than I do say that that's the way it's going to be. So here are our three sets. Now, the important thing is going to be to look at how these functions are going to change. So we're going to look at the derivatives of each of these functions, and that's how we're going to build what's going on. So here's how this model is going to start working. When we look at how the number of susceptible people changes, the thing that you have to try and model here is by thinking about what does the number of susceptible people actually depend on? Well, if we start with more susceptible people, that's going to make a difference versus if we start with less susceptible people. And the number of people that are getting infected is also going to come into play here. So, what's going to happen here is, but we know that as this infection grows, that the number of susceptible people is going to go down because people are getting infected initially. So we know that this derivative starting out is going to be negative. Now, we also would say that this is going to depend on both the number of susceptible people and the number of infected people. Both of those are going to come into a play. So if we multiply those together, that's going to give us an idea of how the susceptibility, the rate of change of susceptible people is going to happen. Now, it's not necessarily going to be exactly S times I. It could be some percentage of that. It could be some proportion of that. And so we introduce this parameter called alpha. And alpha essentially represents the idea that it's kind of like how likely it is that someone who is susceptible is going to get infected. It's kind of like that. It's not exactly a percentage. It's not exactly like that. But alpha is a parameter that sort of signifies this idea. Now, right away, as we build this model for how the derivative is going to work, we have an immediate situation, an immediate problem that we have to introduce a fix for. The problem is that our S function, the number of susceptible people as a function of time, if you think about the range of this function, it would be in a number of people, right? So S represented a number of people. So we might have 137 million people. The units for the S function is people. And the units for the infected function is also people. There could be 10,000 infected people. And so when you multiply those together, like we have in this red equation, S times I, we would end up with people squared. And that's kind of a problem. Like, what is a square person? It doesn't really make sense. What we want to have is the number of people, like, per day, right? We want to have a change in number of people per day. So what we have to do is we have to divide this by the population of people. So what ends up happening is that since we have people times people on the top of the fraction, and then we have people on the bottom of the fraction, it's just going to cancel out one of the units of people. What this also does is it changes our parameter out in the front so that it's really like negative alpha over the population times S times I. And that would be how we can show the change in the number of susceptible people. Now, if we move down to the bottom here and look at the number of recovered people, the idea is that the number of recovered people is going to increase. And it's going to be related to the number of people that were infected. So, for instance, if 10% of the infected people recover or are removed from the infected population every day, then we would want to say, 0.1 times I, 0.1 times the number of infected people would be the rate that these change at. So the expression for this that we get is beta times I, where beta is essentially the rate that, or the percentage of infected people that are removed from that infected population in one way or another each day. So it's like a percentage per day is how that works for beta. So you can see how we have at the top here, negative alpha over n represents kind of how infective this virus is. It's something about the virus that gives us that value. And beta down here at the bottom is also something about the virus. It's how quickly people can recover from the virus that enters into it as well. Now, if we go to the middle, then we're looking at the number of people that are infected. So this comes together pretty well once we have these other two figured out. So, of course, if we're decreasing the number of susceptible people by this factor of alpha over n times Si, then that's going to be the same amount that we increase the number of infected people by. Right? So notice we are decreasing the number of susceptible people by that much, which means we're also going to be increasing, it's a positive value for the derivative here, increasing the number of infected people by the same amount. But at the same time, people aren't going to be infected and stay infected forever. So the number of infected people is also going to go down by the amount of people that are removed from the infected population. So we're going to actually subtract the amount that are removed per day. And now we have this expression alpha over n times S times I minus beta I. So the important thing that you're going to want to notice right away is this number of infected people derivative relies both on the number that are susceptible and on the number that are currently infected. And that's very important. Also, you can picture how there can be a shift in this equation where, because we're adding an amount and then subtracting another amount away, when the amount that we start to subtract gets larger and larger, gets large enough, this will turn around on the graph. And so unlike our exponential function or our logarithmic function, this model is going to allow for that turnaround point in the number of infected so that we can see sort of that curve shape that's happening in our model. So now we want to look at how these derivatives, showing the slope of our three functions, are all going to sort of come together. The problem with this set of differential equations, called a system of differential equations, is that you really can't solve this algebraically. There might be solutions to specific versions of this. It's called a system of nonlinear differential equations. It's a very high-level thing. And it might, most of the time, actually be unsolvable to actually go through and algebraically try to solve it. But computers are very good at looking at billions and trillions of possibilities for the numbers and finding solutions in a numerical way. And so what we're going to do is look at how you can find numerical solutions for this in a minute. But for right now, I just want to concentrate on the slopes of these three things, which are those derivative equations that we just had. So for the susceptible amount, notice we're going to start way up high where everyone in the population is susceptible, but you'd hopefully notice that that derivative was negative, right? It was negative alpha times S times I. The number of susceptible people is always going to be positive, so S is positive. The number of infected people is always going to be positive, so I is positive. N on the bottom there, the population is going to be positive, of course. So overall here we have a negative derivative though, and it's always going to be negative. So the slope of our susceptible curve is that it's always going to be negative. And generally, we start out with just a slight negative, and then it's going to go down and get steeper as more and more people become infected. If we jump down to the removed group, notice that in our removed equation, it's just beta times I for the derivative. So that's going to be positive. That's always going to have a positive slope. Now at the very beginning, it's going to be very slightly positive because we don't really have hardly any people infected yet with which to be removed. But once we end up getting more and more infected, there'll be a little bit of a delay, but we'll also have more and more people removed, hopefully. So the idea is that's going to start down here at 0, and it's going to have a positive slope where it goes up something like this. And then, of course, we'll have our infected graph, which is also going to start very low, maybe at just 1 or 2 infected people. and it's going to have a positive slope initially, but there'll come some spot where the number of people being removed each day is higher in comparison to the number of people that we are losing each day. And so you can see that that will happen right here. There will be a shift. So we can tell that when this shift happens, we should end up with a high spot in our graph. And that high spot right there, the turning point, is going to be the important idea. That's what everybody wants to know, is when is it going to be the highest level of what's going on, right? It's super interesting. So that is essentially the SIR model and how the graph idea operates. You may have seen a lot of this in the news, where it's the idea that maybe the healthcare system can handle that many people at a time. And so the problem is, if we go up above this with our number of infected at any given time, we've gone above what the healthcare system can handle. So as you think through this idea, notice all of this really only depends on two factors, alpha and beta. And so those are the two ideas that are going to be really important to try to figure out correctly, so that we can model this and we can calculate what's really going on. All right, so alpha and beta in the SIR model. So through some research of my own, I've seen that most people that are, generally very knowledgeable about this stuff, more knowledgeable than I am, have determined a value called R naught, and they've said that it's right around 2.5. Now, really, that's sort of a guess, sort of a hypothesis. We're very unsure. They know without a doubt that it's greater than 1, because really you don't even call something an epidemic unless this R naught value is greater than 1. That's kind of the definition of an epidemic. But they think that it's probably greater than 2, and it might be even as high as 3 or 4 or 5. We're really not sure. But we're going to just set this R naught idea to 2.5 so that we can have an alpha and beta to start with. And then my idea of having you model this is I have a couple different tools that I'm going to introduce you to, so that you can try to pick alphas and betas that do this, and maybe you'll change the 2.5 and maybe you won't. The idea is for you to brainstorm ideas and try to get into this modeling idea, but I want it to be accessible to you, at least at first. So to give you some starting numbers, I thought would help. So R naught is just this ratio of alpha over beta from our SIR model that we've already talked about. What I've started with here would be that beta, representing the percentage of people that recover daily, either recover or pass away, people that are removed from the population of susceptible and infected functions. I have set this to begin with to be 1 out of 15. Now, the reason for that is the idea that's been showing in the media a lot about 15 days to slow the spread, I think is what it's called, or 15 days to flatten the curve. And it's the idea that after 15 days, we should be able to see what's going on when we do all of these different ideas. So I'm initially going to set beta to 1/15th, which is approximately 0.06 repeating. And so when I show you the tools that we're going to use, that's the initial amount for beta that I'm using. For alpha then, because alpha over beta, we're having to be 2.5 right now, that turns out to mean alpha would have to be 0.16 repeating. And that number right there represents a very important idea. Because alpha is essentially talking about how likely it is that someone will become infected, someone who's currently susceptible, how likely it is that they will become infected. In a sense, we're saying it's about a 17% chance that a person would become infected. Now, it's not necessarily that exactly 17% or something like that, but it's the idea of this is if we were to raise this number, then what would that mean? And think about that for a second. Raising the likelihood of getting infected would be things like people that are not washing their hands, people that are getting into big groups and hugging and I don't know, they're just not being careful at all. Imagine if we were to lower this number. The ways that we would lower this number are really the social distancing ideas, staying away from other people, hand sanitizer, face masks, all of the things that you've seen in the news, all of the things that people are currently doing are really set up to lower this number. Now, the other number here, the 1/15th, because that is in the bottom of our fraction, what we really want to do with that is we want to raise that value, right? It's the opposite. On this one, we actually want to raise this number. We would much rather that it was 1/8 or 1/7, that a seventh of the people recovered. Or you could picture another way to look at that is people recovered in an average of 7 days instead of 15 days. That would be great. So the way that this one can happen is with therapeutic medications, with different ways of treating people that are already infected, that would make that beta value rise, and that would be a good thing. That would, you can see in the models that when you actually go through the numerical solutions to this on the computer that I'm going to show you, if you change that value for beta, if you make it a larger value, and notice 1/7 is larger than 1/15, when you do that, you're going to actually have the curve be much lower, and it's going to be really a good thing. The infections go down. So I'm going to keep that in mind, that what we want to do with our policies is to lower the number for alpha and raise the number for beta. Now, in the next part, I'm going to show you a simulation that I've made on Google Sheets so that you can pick an alpha and a beta that you think would be a good thing for the model, and then you can look through how that changes the number of susceptibles, the infected, and the removed, and you can look kind of through all of the days because it calculates it for you. And then I'll also show you a website that does really a much better job, but it only shows you the curves that come out, the graphs that come out, instead of showing you the actual numbers of what's going on. So the one that shows you the curves is much more accurate than my Google Sheets version, but the Google Sheets version is there hopefully so that you can learn some interesting things from it.